Okay, now we want to start with y equals the sine of x again, and we're going to consider now y equals a sine of x. Now actually it's not really mysterious what's going on here. When I multiply a function outside by a number, I'm either going to stretch, shrink, or if the number's negative, reflect across the x-axis. But I'll do all these things vertically. And the absolute value of a is called the function's amplitude. Okay, so this is fairly straightforward. If I have y equals 2 sine of x, and I start with my graph just of sine. Okay, so here's my graph of sine. There's one period, and I can extend this, right, both ways. Here's pi, here's 3 pi over 2, here's 2 pi. So this would be 1, negative 1. Now, what's going to happen to my y values here? Well, my y value at this point is 0, and the thing is then 0 times 0, 2 is still 0. But here, at pi over 2, sine is 1, so 2 sine pi over 2 is going to be 2. So I'm going to be up here now at 2. Now I would see this as well if I made a table here. But I'm going to be increasing up till here, and then I'm going to decrease, and then instead of going down to negative 1, we'll go down to negative 2 here. Right? So 3 of my 5 points of interest stay the same. These other ones are stretched. Okay, so that's a stretching. What if I have, for example, y equals 1/3 sine of x? Okay, then what? Then again, I start with my sine function, right? Like so. So there's one period. But now my y values are going to be shrunk by a factor of 1/3. So I'm going to have be up to a third, down to a third, right? Negative 1/3 for these 2 points, and all the other points are the same. So this is shrinking here. Now, it might seem to you a bit unfair with the previous video is that it was the opposite. When we were multiplying through by 2, for instance, when we had sine of 2x, it actually shrunk horizontally. It didn't stretch. Why are we stretching vertically here? It doesn't seem right. Well, the reason is that my 2 here is on the outside. And so this is something that we might note here, is that we can write y equals 2 sine of x as 1/2 y equals sine of x. And if I write it in this fashion, it's not so mysterious that we're doing the opposite thing of what you might think. Okay, finally, if we have a negative value, that's going to reflect about the x-axis. If I have y equals negative sine of x now, just think all my y values are negated. And when I negate a y value, I flip it across the x-axis. So instead of being up here at 1, we're going to be down here at negative 1. And then, so that's that point. And then over here, instead of being at negative 1, we're going to be up here at 1. So my y equals negative sine of x, just in general, is going to look like this, right? and so on. So you have to use your imagination here a little bit in order to do that. What we might do is combine this with our previous one, and we'll do that in the next video. Okay, now I want to think about graphing some transformations of the sine function. So if y equals the sine of x now, this has period 2 pi, and so we have 0, pi over 2, pi, 3 pi over 2, 2 pi here, and down here is negative 1, and up here is 1. So I have these points of interest here that I'm going to have my curve through, and I might have something like this. Of course, this 2 pi here, and then this repeats, forever and ever, the period of 2 pi. And what I can think about now is some transformations of sine. And the first one we want to think about, in fact, is y equals the sine of bx. And what b is doing when you replace x by bx in a function, it's going to stretch or shrink your graph horizontally. And we can see that with perhaps an example. So let's say we have y equals the sine of 1/2 x. I can make a table if I want and see that my x values have to be twice as large to give us the same y value. So here's 1/2 x. Here's going to be sine of 1/2 x. This is x. So half x is going from 0 to pi over 2, pi, 3 pi over 2, 2 pi. So half here is going to be 0, 1, 0, negative 1, 0. But if this is a half x we're feeding in here, x has to be twice as large as these values. So I have 0, pi, 2 pi, 3 pi, 4 pi here. My x values have to be twice as large to give me my same y values. And the period here is going to be 2 pi over 1/2 is 4 pi. And so 1/4 of the period is going to be just 4 pi over 4, or pi. And that's where I have these guys evenly spaced pi. These up here in sine are evenly spaced too, but here 1/4 of the period is pi over 2. So I have 0, pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, if I don't simplify. And now we can graph this and see our points of interest here. So now we're going to have 0, pi, 2 pi, 3 pi, 4 pi, and then I have negative 1, 1. I'm just going to sketch one period of this. And so I'm going to have something like this, and which, because of scaling, it might look like another one. And then again, this keeps going off there, and this is going off to that end too. So if I want to graph that one period, I can. And we can think about what happens in general here if with the sine of bx, and b is between 0 and 1, then we have to, for the graph of this, we have to stretch. So for the graph of this, for the graph of this function, we must stretch the graph of y equals sine of x by a factor of 1 over b here, right? So, in fact, our period here for y equals the sine of bx is what? It's 2 pi over b in general. So if I want a quarter of the period, it's going to be pi over 2b. Okay. And so you say this is going to work not only for b as a half, b as a third, b is 0.7. All of these are going to stretch this or stretch this horizontally by a factor of b. Well, not factor b, factor of 1 over b. Okay, let's do another example here. So now we want to consider, for example, y equals sine of 3x. I want to think about what this is doing. Well, the period here is 2 pi over 3. So 1/4 of the period is going to be what? Well, 2 pi over 3 divided by 4 will be 2 pi over 12 or pi over 6. And this means that my points of interest are evenly spaced pi over 6 apart from each other. So I have 0, pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6. Right? And so I didn't simplify here, so I wanted to show that these are evenly spaced. Right? This last one here, this is 2 pi over 3. Right? And right here, this is pi over 3. But for the sake of my graph here, I'm going to have my points of interest here again are those 5 points, which I can graph like so. Okay? And so what do I get this graph here? My graph is shrunk by a factor 1/3. The reason being that my x's have to be 1/3 of their old values to give me the same y values. Again, if I want to think in terms of a table, I can. So here would be 3x, and then here would be sine of 3x. Well, I know what this table looks like. This would be 0, pi over 2, pi, 3 pi over 2, 2 pi. So this would be 0, 1, 0, -1, 0. But my x's here have to be 1/3 of this. So I have 0, pi over 6, pi over 3. And then here I'm going to have what? Pi over 2. And then here I'm going to have 2 pi over 3. Right? And again, what is this? This is 0. This is pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6. Right? If I don't reduce, I see that all these guys are evenly spaced. And they have to be 1/3 of what they were so that my sine value, I get the same value up here. And in general, if b is bigger than 1, we're going to shrink by a factor 1 over b. So if b is bigger than 1, we want to shrink the graph of y equals sine of x by a factor 1 over b. So no matter what b is, if I have y equals the sine of bx, the period is 2 pi over b, and 1/4 of the period is going to be pi over 2b. I divide. Okay, and that's that. Okay, so here I want to do an example of graphing a sine function of this form, y equals a sine bx minus c plus d. This is my first example here. It's just y equals this. And we just build this up from basic things. So, start with the sine of x, right? And the sine of x we know looks like so. This is one period. I'm just going to do one period for these things today, and then you can extend it either to the right or left as you want. But the period here for this guy is 2 pi, right? So 1/4 of the period is pi over 2. And I have these points of interest. Here's 0. This is pi over 2. Here I have pi. And here I'm down here. I have 3 pi over 2. And here's 2 pi. So I have these 5 points of interest, so to speak. And it's ranging from 1 and down here -1. And this will repeat then in 2 pi in either direction here. I might also notice this is, if I didn't simplify, this would be pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. These are equally spaced. And now first of all we want to think, what does this 2 out here do? Well, the 2 here is going to stretch this vertically by a factor of 2. Okay, here I want to sketch a few examples of the sine function of this form. Y is a sine bx minus c plus d. I'm going to start with this, and we'll just go through this and maybe a couple more examples. I'm going to mainly draw one period, and then you can extend it along the x or x-axis period of whatever the period is. So I'm going to first consider my sine of x, and its period is what? Is 2 pi. So 1/4 of the period is pi over 2. And it's my graph of just the sine function here. One period of it anyways. I'm going down from -1 to 1 here. Then here would be pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. If I thought about these just in periods, of course, this one we simplify. This is, of course, pi. And this one here is, of course, 2 pi. Right? But I'm just going to be, time and time again, drawing 5 set points of interest to see what's going on. So for this sine of x here, we started at 0, 0. Then we're up here, then here, then down here, and then up here. I have this nice smooth curve, like so. Like I said, the period's 2 pi, so you extend this in either direction. So the first thing we want to do when we do this is maybe think about the 2. What does this 2 out here is, right? So I'm going to have my sine of 2x. So now what we want to think about is, what does y equal 2 sine of x look like? And in general, the coefficient for the sine here, this a here, is called the amplitude. So my amplitude here is 2. The period is still 2 pi. 1/4 of the period is pi over 2. And what does this 2 do here? The 2 here is going to stretch the graph of sine vertically by a factor of 2. So basically, instead of going up from negative 1 to 1. We're going to have our points, but now think about this. If I put 0 in here for sine, I still have 0. At pi over 2, though, sine of pi over 2 is 1, so this is going to be 2, so it's going to be up here now. Okay, and then at pi, or 2 pi over 2, I put this in here. Sine of pi is 0, so I'm back to 0. And then I have my 3 pi over 2, and likewise going to be down here. And then my 2 sine of 2 pi is 0. So I have my previous graph, but now it's stretched vertically by a factor of 2. Okay, now we want to think about what the 3 does. So now I'm considering y equals 2 sine of 3x. And we've seen what the 2 does. The 2 stretched the original graph of sine vertically by a factor 2. The 3 here, I claim, is going to actually shrink the graph horizontally by a factor 1/3. And you see our amplitude here is 2. That's how far up and down it's going. And then the period, well, the period in general is going to be 2 pi over b. So here I have a 2 pi over 3. And so 1/4 of the period I know is pi over 6, right? Just multiplying this by a quarter. And in general, the period is this, the amplitude is this, and we want to sketch this thing and see what it looks like. And I'm not going to have the same scale as before. I'm going to go from, down here, negative 2, up here is 2, and here I have pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6. Okay, and this is 0. So again, these points of interest are evenly spaced here, and at 0 I have 0. If I put pi over 6 in here, I'm actually going to have the sine of pi over 2. So put pi over 6 in there. 3 times pi over 6 will give us pi over 2. Notice that I had to shrink by a factor of 1/3 horizontally to get the pi over 2. So at pi over 6, I'm going to be up here. 2 pi over 6 here. 3 pi over 6 here. And 4 pi over 6 there. And so this is what my graph there looks like. And then I can extend this in either direction according to the period. Okay, now we want to see if we have y equals 2 sine of 3x minus pi over 2, what this c here does. Now, c is affecting x, which is the horizontal variable, but we're not shifting over by c right or left because of this b here. We have to take that into account. And so first what you have to do is factor the b out of there. So if y equals 2 sine, you have a 3 times x minus, this divided by 3 is pi over 6, right? And you can see that because if you distribute this, 3x is 3x, 3 times pi over 6 is pi over 2. So you can get that. Now what's this do to our graph? What it's going to do, it's going to shift it over to the right, pi over 6. So if I come back to the graph I had before, I can see how that works. And basically, before we had this, right? But now I'm going to have here, okay, so this is, I'm putting in this, minus pi over 2 here, and it shifts over here. So here I have that shifted, that,
that, and then I'm half point there off of the grid. But you see how that, so this is going to be my graph of y equals 2 sine of 3x minus pi over 2. Okay. Is that good? Anyways, finally we have this d up here, and for that we're going to shift vertically up if d is positive and down if d is negative. So if I'm adding 2 here, basically what's going to go on here, so here's 2, here's 4, here's negative 2, negative 4. I still have my 0, my pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6. But now I need to have another 5 pi over 6 here because I had shifted this. So now look at this graph up here. I'm going to add 2 to all of these coordinates. So at pi over 6, instead of being up here at 2, I'm going to be up here at 4. Now, at pi over 6, instead of being at 0, I'm going to be up here at 2. Right? And then at 2 pi over 6, instead of being at 2, I'm going to be up at 4. And then at 3 pi over 6, instead of being 0, I'm up at 2. At 4 pi over 6, instead of being at negative 2, I add 2, I'm at 0. And then at 5 pi over 6, I'm back to 2. So my graph looks something like this. You have to use your imagination. And you might notice that we have this symmetry about line y equals 2, right? And the amplitude we're going up and down to, right, off of that. I had stretched vertically by a factor of 2 and shrunk horizontally by a factor of 3. And then again, you can extend this either way using just copying it, right, because of the period.